Hi everyone, welcome to CAIE Science. Today we will be solving the remaining paper of the October-November 2002, October-November 2022, parent 41 and 43 9701. Last time we did 5 questions. Today we will start with question number 6. So let's begin. Question number 6. An aqueous solution of copper to sulfate is a blue color due to the presence of this complex ion. Write an equation for the reaction between this complex ion of copper and sodium hydro. So when the OH ions will react in this sodium carbonate. So what is going to be the equation? Equation is going to be this complex ion will react with OH ions, and OH ions will replace the water ligands. Okay, so this will be like, by the way, you have to remember these equations. Okay, these equations of these complex ions. Okay, so two of the water ligands are substituted by OH ions. Okay, that's your equation, and you can see that in this complex the charge is 2 plus because water has no charge and the oxidation state of copper is plus. So overall the charge on this complex is 2 plus, but you can see that OH ions have charge of 1 minus. So there are two OH ions, so the 2 minus charge will cancel out this 2 plus charge on this copper. Okay, so the overall charge over here is 0. Okay, you have to also remember these, what will be the charge on this complex. Okay, now moving towards next part. Write an equation for the reaction between this complex ion of copper and an excess of concentrated HCl. So when complex reacts with chloride ions, actually the chloride ions, Cl minus ions, are bigger, so the geometry of this complex will change. Okay, the geometry will change from the octahedral to the tetrahedral. Okay, okay, that's going to be a structure, and chloride ions have charge of 1 minus, and there are 4 chloride ions. So and the charge on copper is 2 plus, so 2 minus 4 is equals to 2 minus, so the charge over here will be 2 minus plus 6 water molecules. Okay, also have to balance here. So these equations you have to remember, and you also have to remember the colors of these complexes. Okay, now moving towards B part. An excess of ammonia is added to the solution of copper, this complex of copper. A deep solution containing this complex ions is formed. There are two possible stereoisomerism, the formula of this complex. Complete the diagram. So the stereoisomerism in the boxes below. Stereoisomerism. Now there are 4 ammonia ligands and 2 water ligands. So this will show a geometrical isomerism. Why? Because in these complexes, the cis has a bond angle of 90 degree and trans has a bond angle of 180 degree between similar ligands. So let's see. Let's say I'm first drawing the this cis, cis isomer. Okay, let's draw this cis first. So this is going to be your cis isomer, and you have to take it by the reference of water, because there are two water molecules, so it is easy to check by the reference of water. So you can see here that the bond angle between both water molecules is 90. So this is polar, trans is non-polar. You also have to remember this as well. Now, and you can also see that the bond angle between this water molecule and this ammonia is 180 degrees. So the polarity of this ammonia and water is different, so it will be a polar and it will be a cis. Okay, but on the other hand, you have a trans, and trans will be in trans we will have water molecules at an angle of 180 degree, and then we have ammonia. So you can see that in cis the polarity does not cancel out, and in trans polarity does cancel out. These ammonia cancel out with this ammonia cancel out with this ammonia, and this water molecule is out with this water molecule. The overall polarity is uh, cancel out. Okay, so it is non-polar. Okay, I hope you understood. And here you can see that the polarity is not cancelled out. Okay, now, so these are your structures, the possible isomers. Okay, this is this, and this is trans. You are not required in this part tell whether it is a cis or trans. You just have to draw this. Okay, now in the second part, use your answer to b1 to deduce whether each of these isomers is a polar or non-polar. Now you know, I already told you that the cis is polar and trans is non-polar. So which one of this is polar? So which one of this is polar? Polarity of isomer 1. So this is a cis. Okay, so cis. Yes. Use your answer to b1 to deduce whether each of these isomer is a polar or non. So isomer 1 is a cis isomer, so polar. Oh, sorry, you can write as polar. Sorry, as polar, as polar. Okay, and trans as non-polar. Okay, this is your answer. Now, the numerical value of the K stability of this complex ion is 1.4 into 10 to the power 13, and this is a high K stability value. Okay. Define the stability constant. It is the equilibrium constant for the formation of complex. Okay, so let's write the definition. The equilibrium constant is the equilibrium constant is the constant. You can write there as the is the equilibrium constant. Yes, let's rewrite this to show the answer. It is the equilibrium constant for the formation of complex ion in a solvent from its constituent ions. Okay, from its constituent ions. Okay, or molecules. So this is the definition of stability constant. You have to remember this. Okay. Compare the stability of this complex and this complex. Explain your answer. Okay, so you are given the value of this complex, the ammonia complex, but you are not given the value of this complex. But you can see that if ammonia is reacted, this complex change into this complex. So it means this complex is more stable. That's why copper formed this complex when ammonia is added. Okay, so you can say that this complex is more stable. Okay, because it has a greater K stability value. Okay, so you can set this complex of copper is more stable because or as K stability is larger. Okay, larger the K stability value, large and the stable the complex. Okay, write an expression for the K stability of this complex and state the units of stability constant. So how this complex is formed? When this complex, the initial complex of copper, reacts with ammonia, it forms this copper, this complex of copper. Okay, so what will be the equation? Okay, now there are 4 ammonia over here. Okay, balancing the equation is a must. Okay, now write the K stability value. So K stability is actually the ratio of the concentration of products divided by concentration of reactants. So now the product is this. So K stability is going to be the concentration of this complex of copper which is formed concentration of this complex divided by concentration of this complex of copper and concentration of ammonia. Okay, and ammonia has 4 moles, and so moles will be in power, you know that. Okay, now you have to state the units as well. Okay, units. So what will be the units? uh, Here you will have a unit of mole per dm cube. Okay, and down in denominator you have mole per dm cube multiplied by mole per dm cube power 4. Okay, so this dm cube cancel out with this dm cube, so you will have a finally mole minus 4 dm cube 12. Okay, so these are your final units. Okay, let's move to the next part. In a particular solution, the concentration of this complex ion is 0.07 mole per dm cube and the concentration of ammonia is 0.57. Use your expression in CT and the K stability value. This is the K stability value which is also given to you to calculate the concentration of this complex. So you are the given here, you have to use this expression. So the K stability value is given to you 1.4 into 10 to the power 13 is equals to, and you are also given the value of a concentration of this uh, complex, so which is 0.0074 divided by, you are given also the concentration of ammonia which is uh, 0.57 power 4. Now you just have to calculate the concentration of this complex ion. So you can calculate easily from this equation the concentration of this complex ion, and which is going to be 5.01 into 10 to the power minus 15. Okay, this is your final answer for this part. Okay, 5.5.01 into 10 to power minus 15. Okay, let's move to the next part. Phenanthroline and ethanediol are bidentate ligands. Okay, ruthenium 3 forms an octahedral with phenanthroline and chloride ions. Okay, the complex ion contains two phenanthrolines. Okay, molecules. Iron 3 molecule forms an octahedral complex with ethane diode ions. Reduce the formula and the charge for each of the complex. Lithium forms a complex with phenanthroline and both chlorides, which has a geometry of octahedral, and there are two phenanthrolines. So two phenanthrolines will each phenanthroline will uh, donate two of its lone pairs. So two phenanthrolines will donate four lone pairs of electron, and there are two chlorides. So in total, you have six ligands. Okay. So you are given the formula for phenanthroline. So what will be the formula for this complex? Lithium. Then you have phenanthroline P2C12H8 N2. There are two. Okay. And then you have Cl2. And then what will be the charge, overall charge? It is going to be the +1. Why? Because there is no charge on this phenanthroline. You can see that. But the charge on chloride is 1 minus, and there are two chlorides. So the overall charge will be on overall charge on chloride will be 2 minus, and the lithium has a charge of 3 plus. So the overall charge will be 1 plus. Now for the complex iron 3, you have ethane diode. It forms octahedral with ethane diode ions only. So there will be three ethane diode ions. Okay, C2O4 3, because this is a bidentate ligand, so it will form three. Three, uh, three molecules will form octahedral geometry. So now what will be the overall charge? It is going to be the 3 minus, because the charge on ethane diode is 2 minus, and there are three ethane diodes. So it is minus 6, and the charge on iron is 3 plus. So 3 plus minus 6 is minus 3. Okay, so the overall charge is minus 3. So these are your structures for the complexes. Now question number 7. The structure of compound P is shown in figure 7.1. P is optically active. Use an asterisk to identify all the chiral carbons atoms on the structure of P. So chiral carbons are where there are no double bonds, and carbon is attached to 4 different groups. So the ring will not have a chiral carbon, because the ring has a carbon carbon double bond. Okay, and this carbon will also not form chiral carbon, because this is a double bond with oxygen. So only this carbon, which is attached to 4 different groups, and all the four groups are single bonded. So this is a chiral carbon. It is the only chiral carbon. This can't be chiral carbon, because this has 2 hydrogens. Okay, so this is the only chiral carbon. You have to put asterisk over there. Now plain polarized light is passed through the pure sample of 1 enantiomer of P. This is then repeated with an pure enantiomer of pure sample of other enantiomer of P. Okay. Enantiomers are actually the mirror images of each other. Compounds which are mirror images of each other. Describe the results of these two experiments, stating the similarities and differences of these results. So optical isomers rotate the plane of polarized light into opposite direction, okay, but by same angle and in the same direction. Okay, so what will be the similarities? Plane polarized light will be rotated by same angle, by same angle, sorry, by same angle, um, and but in but in opposite directions. Okay, but in opposite direction. So that's your answer. Now part B. P can be used to make Q in a single step. Okay. Give a reason, give the structure formula of the compound that is added to P to make Q, and give the formula of the other product of this reaction. Okay. So the what is the reagent that is added to P? So let's copy P. Let's move all this. We have this over. So I'm just trying to make this. So okay, forget this. Let's focus the question. Okay, so this P. Okay, um, we have this. Now you have P. So this P is changed into Q. Okay, so what is added? You can see that this amine group over here um, is actually this amine group is actually one hydrogen of this amine group is changed with this group. So this is actually polyamide, sorry, amide linkage, and amides are formed from the acyl chlorides or acyl halides. Okay? Acyl halides, or you can say acyl chlorides. So this will be the other compound which is added to Q will be 1 2. So it will be ethanoyl chloride, and it is a formula of CH3 COCl. Okay, so this is the compound which is added to the this CO this P. Okay, COCl. When COCl CH3, this double bond Cl will react with P, it will form Q plus HCl. Okay, the hydrogen, the one hydrogen that is removed from this P reacts with the chloride ions to form HCl. So the other product is HCl. Okay, part 2. When an ester is treated with LiAlH4 in dry ether, the ester linkage is cleaved by the addition of 4 hydrogen atoms and 2 alcohols are produced. Draw the structure of compound formed when Q is treated with an excess of LiLH4 in dry ether. So this is Q. Okay, and when this Q is reacted with excess of LiLH4, it will form uh, the this amide group. When this reacts, this amide group will change into the alkanes. Okay, the carbon double bond oxygen, the carbon which is double bond to oxygen will change into CH3 group. Okay, you have to remember this. This was a little tricky part. So what is going to be your final answer? And this, by the way, this ester linkage will also break down into this methanol, and this this carboxylic acid will further reduce to alcohol. So the final structure is going to be like this. Um, This is your final structure. Okay, NH, and you will have other structure of OH, which is methanol. Okay, so you can see that this OH, this carbon oxygen double bond is changed into this CH2 group. Okay, this is the main weight part. Okay, you have to remember this, that this amide group, and this reacts with LiAlH4. LH4, it forms CH, CH, NH. Okay, this was an important part. And this ester group changed into carboxylic acid, and the carboxylic acid further reduced to alcohol because the excess of LiLH4 is used. Okay. Now to compare the relative basicities of compound P, Q, and phenylamine. Okay, so the structure of phenylamine is this. This is the structure of phenylamine, and you have then Q, and you have P. So basicity. So basicity actually depends on the basicity depends on the availability of lone pair. So the in Q will be the least basic because the lone pair on on nitrogen will be delocalized in this group. Okay, this amide group. This will be delocalization of the lone pair on nitrogen in this part. Okay, so you have also learned that amides are least basic or not basic in nature. Okay, or very less basic. So Q, you have a Q over here. Then and then you will have a phenylamine. Okay, because in phenylamine this lone pair on nitrogen will delocalize into ring. Okay, so phenylamine, and then you have P. P is most basic because the you can see in P that the lone pair on this nitrogen um, okay, the lone pair on this nitrogen and is attached to alkyl groups. Okay, and alkyl groups are electron donating groups, so they will generate a positive inductive effect. So the lone pair density on this ammonia on this nitrogen will increase. Okay, now let's your answer what the reasons. Okay, so basicity basicity depends depends on ability of nitrogen to donate its lone pair to a proton. Okay, so now uh, in phenylamine lone pair in phenylamine lone pair is delocalized into ring. Okay, and in the in the Q, the lone pair, and in Q lone pairs. Okay. In Q lone pair is delocalized by carbon oxygen this bond. Okay, carbonyl group. Okay, and in Q and in P alkyl group alkyl groups or alkyl group has a positive has a positive inductive effect. Okay, so these are your reasons. Inductive effect. That's why the Q is least basic and P is most basic. Now part C. P can be used to make compound R in two-step reactions. Okay, shown in figure 7.2. To identify the reagents and conditions used for the two steps of the reaction. Okay, so now this ester group is changed into this carboxylic group, and there is another amine, phenylamine is formed. Okay, so in first step, let's say you reduced this, you hydrolyzed this ester to form the to form this this carboxylic group. Sorry. So what will be the conditions? So you hydrolyze a ester by concentrated sulfuric acid. Okay. So when this concentrated sulfuric acid is used, okay, let's make this. Okay, concentrated sulfuric acid, concentrated nitric acid, and H2SO4. Okay, this concentrated H2SO4 will uh, hydrolyze this ester to carboxylic acid, and there will be a nitro group attached. Okay, due to this nitric acid. And in second step, we will reduce this nitrobenzene to form phenylamine. Okay, and what are the conditions for this? This is thin and concentrated HCl. Okay, and heat under reflux. Heat under reflux. Okay, so these are your conditions. Now let's move to the next part. Complete the table 7.1 by drawing the structures of the organic products formed when R is reacted separately with the reagents given. Okay, HNO2. So this will form an azodide R. Okay, so this phenylamine will form an azodide. So let's draw this. This will form, this phenylamine group will change into this azodide group. You have to remember the diagram or your structure of this azodide. Okay, and this will have a positive charge. So this is the azodide group, diazonium group. Okay, diazonamine. This is the diazonamine. Okay, and then in next step, an excess of bromine at room temperature. So when excess of bromine is added to R, the bromine will actually attach to 2, 4 and 6 positions, but on 4 position you can see that this alkyl group is attached, so only on the 2 and 4 positions bromine will attach over here. Okay, so this is your final structure. There will be an amine, and you have to also remember that this amine, this phenylamine is 2,4 director. Okay, 2,4,6 director. Br over here, Br will also be over here, and the rest of the structure is same. Okay, so these are your structures. Okay, let's move to the next part. P can be used to produce T. Okay, in an aqueous solution, T has a property called isoelectric point. Explain what is meant by isoelectric point. So it is a pH where the species is a zwitterine. Okay, So pH at which species species is, or you can say the pH where the uh, species is Zwitterion. Okay, species is Zwitterion. You can also write that, or you can say that their pH at which species has no overall charge. Okay, you can also write that as well. So part 2, tea can be polymerized under suitable conditions. Okay, no other monomer is involved in this reaction. Draw a section of polymer chain formed that includes 3 T monomers. Identify the repeat unit. So this T has amine group and this carboxylic group. So this will form amide linkage, and this will be your polymer. Okay. So let's make let's say let's draw this structure a little. I'm just writing this structure to make this a little more easier to draw the complex. So this will be sorry TH. So I have just redrawn this structure to make it easier for us to make the complex ion. Okay, so the structure will be like this. Okay, I have just redrawn the structure of T. So now when the T will form the polymer, this H and this OH will remove and the omide linkage will form. So the repeat the polymer formed will be like this. This TH. Okay, this CH and H, and this will form a carboxylic group like this, and then you will have a CH, sorry, like this. Then you will have a ring like this. You have to show the 3 monomers, okay, or 3 repeat units. Identify the okay, and that includes 3 monomers. Okay, so 3 monomers. You have to further draw it um like this. CH and another ring like this. So this is your polymer. Okay, you can see. And what will be the repeat unit? You also have to show the repeat unit. So you can see that this part is repeating. Okay, you can see from the this polymers that this part is repeating. So this is your repeat unit. Okay, repeat unit. Now moving towards question number 8. Benzene is an aromatic molecule. State the carbon-carbon-carbon bond and the hybridization shown by the carbon atoms in the benzene. So hybridization in the carbon is sp2 because each carbon forms a carbon double bond and the bond angle is 120 degrees. You have to remember these properties of benzene. Part B. Benzene reacts with chloroethane in the presence of catalyst. The reaction mechanism is called electrophilic substitution. The first step in the reaction is generation of this electrophile. Write an equation for the reaction that generates this electrophile. So chloroethane, when chloroethane CH3 CH2 Cl reacts with LCl3, this is the catalyst. Okay, this is your catalyst LCl3. So it will generate an electrophile, this electrophile plus LCl4 minus. Okay, Describe the mechanism for the reaction between benzene and this electrophile. Okay, include all the relevant curly arrows and charges. So this electrophile will be attacked by the benzene ring. Okay, this benzene carbon carbon bond, because this carbon carbon double bond has a high charge density, so this will attract this electrophile, incoming electrophile. So this electrophile will attach like this, the structure of intermediate. This will be like this, H and CH2, CH3, and then this hydrogen will donate its electrons and it will form H plus ion. Okay, so the final structure is going to be like this: CH2, CH3 plus H plus. Okay, so this is your final answer. Okay, so this is your mechanism. You have to remember these mechanisms. Okay, part C: chlorobenzene and chloroethane have different reactivities in the nucleophilic substitution reactions. Okay, identify a suitable reagent to illustrate the difference in the reactivity. The reagent chosen should be visibly different. It should give a visibly different results with chlorobenzene and chloroethane. So in chlorobenzene, this is your chlorobenzene. The lone pairs on this chlorine delocalize into ring, so it forms a stable compound which this forms a partial double bond with chlorine. So this is more stable. Okay, this bond is not easier to break down. Okay, so this chlorobenzene will not react with silver nitrate. Okay, so it will not react with silver nitrate, but the chloroethane can react with silver nitrate to give a white ppt. Okay, so now write an equations to describe any reactions that occur. So the best way to show this is to write when this chloroethane reacts with firstly NOH, it forms P2H5OH plus NaCl. Then this ethanol, not this ethanol, this NaCl. Now when this NaCl reacts with silver nitrate, it forms sodium nitrate plus silver chloride, which gives a white ppt. Okay, so this is the reaction which happens, and no equation for this chlorobenzene, because the chlorobenzene does not react with the edges so silver nitrate. Okay, now moving towards next part, explain the difference in the reactivities of chlorobenzene and chloroethane in nucleophilic substitution reactions. So difference, what is the difference? The lone pair, you can write that the lone pair uh, this lone pair from Cl overlap with benzene ring. Okay, so it forms a stronger partial double bond. Okay, you can write that as well. So the lone pair from chlorine Cl overlaps with benzene ring, and you can say it forms a carbon carbon double bond. Okay, and forms partial double bond. Okay, partial double carbon Cl bond. Okay, You can write this as well, or you can write that this TL bond is then difficult to break. Okay, you can also write that as well. Now I think this is your last question. Yeah, this is your last question. Question number 9. Okay, so question number 9, part A. Gas liquid chromatography involves a stationary phase and a mobile phase. Okay, name or describe in detail a suitable substance that could be used for each phase. Stationary phase. So stationary phase is actually a non-volatile liquid. Okay, non-volatile and non-polar liquid. And mobile phase in gas liquid chromatography, you have to remember this, it is an inert gas. So any inert gas, or you can write a named inert gas. So let's say I'm writing argon over here, and the stationary phase should be non-volatile volatile liquid. Okay, you have to remember the stationary phases or mobile phases for gas liquid chromatography, and layer chromatography, and paper chromatography. A mixture of three organic compounds is separated by a gas liquid chromatography. The chromatograph gram obtained is shown in figure 9.1. Amount of each substance is proportional to the area under peak. Okay, explain the meaning of retention time. So it is the time between injection and detection. The time between injection and detection. Or you can also write that it is the time that the substance stays in the column. Okay, now part 3, calculate the percentage of B in the mixture. Show your working. So percentage of mixture, so you can also actually uh, calculate this record response as their amount. Okay, so let's say this B has amount of 100 and this A has amount of 30, then this C has amount of 25. Okay, so you can say that the areas are A is equals to 30, B is equals to 100, and C is equals to 25. So in total, 100 plus 30 plus 25 is equals to 155. Okay, um, yeah, it's 155. Okay, so you have to calculate the percentage of B in the mixture. So the mass, the amount of B is 100 divided by 155 multiplied by 100. So you will get the final answer of let's calculate this, divided by 3, 155. So you will get the percentage of 64.5. Okay, so 64.5 percentage of B in the ejection mixture. Now moving towards next part B. Complete the table 9.1 to give the number of peaks in the carbon 13 spectrum of each of the 5 isomers of C5H10O2 that has a ester group. So let's first draw the structures of these ester. CH3, CH2. Let's open this carboxylic group OH, CH3. So you can see that this carbon has a different environment. This carbon has a different environment. This carbon has also a different environment. From here, 1, 2, 3, 4, 5. So 5 environments. So 5 peaks will be shown. Okay. Now for the second part, 1, 2, 3. Let's draw the structure of this as well. CH3, CH2, C double bond, CH2. CH3. And let's draw the structure of this as well. CH3, C double bond O, CH2, CH2, CH3, and then this CH3, H plus CH3, C double bond O, CH3, and then finally CH3, C double bond O, CH, uh, CH, CH3. So now let's count the number of peaks in each. So one, oops, so 1, 2, 3, 4, 5. 5 peaks shown will be five peaks will be shown here. Now in this part, 1, 2, 3, 4, 5. 5 peaks will also be shown here. And this carbon, these both carbons have same environment, and this carbon has a different. So 1, 2, 3, 4. 4 peaks will be shown here. And these two carbons have same environment, and this carbon has different environment. Okay, so 1, 2, 3, 4. 4 peaks will be shown here. Okay, now moving towards next part. Check the number of peaks that would be seen in the proton NMR spectrum of methyl butanoate. Name all the splitting patterns seen in this spectrum. So let's draw the structure of methyl butanoate. CH3, CH2, CH2, C double bond O, and this is the structure of methyl butanoate. Now let's count the environments of hydrogen. Okay, so number of peaks. Okay. You have to show the, so this hydrogens have different environment. Then this hydrogen also has a different environment. Then you have this hydrogen. This also has a different environment. Lastly, you have this hydrogen. These hydrogens also have a different environment. So you have 4 different environments. So 4 different peaks will be shown. Now you also have to tell all of the splitting patterns that will be shown. So there will be a singlet due to this, because there is no hydrogen on the adjacent carbon. So singlet. Then you will have a triplet as well, due to this these hydrogens, because they have 2 hydrogens on the adjacent carbon. Okay, so triplet, and due to this these hydrogens will have a quartet or multiplet. You can say multiplet or quadrat, you can say, because on the adjacent carbon you can see there are 3 hydrogens here and 2 hydrogens over here. So it will show multiplet. Sorry, multiplet. So multiplet. Okay, so these will be your splitting patterns. Now moving towards the next part, part D. The D and E are both esters with the molecular formula C5H10O2. Their proton NMR spectra are shown in figure 9.2 and 9.3. Okay. Now deduce the structures of 2 esters. Okay, you have to deduce the structures of 2 esters D and E and draw their displayed formula in the boxes shown. Okay, so let's first analyze D. By the way, these numbers show you the the hydrogen which is responsible for these peaks. Okay, number of hydrogens which are responsible for these peaks. Okay, now you have a triplet and the number of hydrogens responsible for this. Okay, so and there are two triplets, so you can actually say that let's say there are two two CH3 groups. There will be two CH3 groups that will be attached to CH2 groups, because this CH2 CH3, these hydrogens, these three hydrogens will show triplet, because there are two hydrogens on the adjacent carbon. So these all three hydrogens will show triplet. Okay, okay, and you can also see from the table that peak in this chemical shift is due to alkane. Okay, so this CH, so you now, and there are two peaks like this, so there will be two these groups CH3 CH2. Okay, so two groups that will there will be two CH3 CH2 groups. Okay, now let's move further. You have a quartet and you have two hydrogens. Okay, now let's first analyze which uh, which compound gives the peak in this environment. Okay, there will be no aromatic ring, because it already told you that these both are esters, so there will be no aromatic compound, so this will not be the environment. So this will be the environment, carbon, this carbon double bond oxygen. Okay, this is in the chemical shift of 2.2 and 3. So this will give a chemical shift number of carbon which are number of hydrogens which are responsible for this quartet is 2. So what you can say actually that this this carbon, this carbonyl is attached to you can say two hydrogens. Okay, and on this uh, and on adjacent, you can see from this table, yeah, yeah, you can see that this will be the group. Okay, number of hydrogens that are responsible for this peak is CH2. This will be the your structure, and they this shows a quartet, so the number of hydrogens on the adjacent carbon will be 3, because this shows a quartet. Okay, and number of hydrogens which are responsible is 2, so this is your this will be your structure. So and in now at last you have this hydrogen environment. Okay, and this has also shows you the quartet, and there are two actually hydrogens responsible for this peak, so the final structure is going to be like this. Okay, so this is your structure for D, which is CH3 CH2 C double bond O, and this ester linkage, and then CH2 CH3. So I already told you that there will be two CH3 CH2 groups, and you can check this D by further analyzing it, but this will be the structure. Okay, final structure of D, sorry. Now let's also analyze the structure of E. So E has a doublet, and 6 hydrogens are responsible. So you can imagine that it could be like this: CH and CH3. So these 6 carbons will have this doublet, because there is one hydrogen on the adjacent carbon. So these 6 hydrogens will show um, like this doublet. Okay, you can see, you can imagine that. Okay, and you can also see that this in 0.9 to 1.7, this chemical shift is due to alkanes. Now this peak, okay, this number of hydrogens which are responsible for this peak is 1. Okay, so you can see that this carbon, okay, number of carbon, this hydrogen, okay, this hydrogen has 6 hydrogens on the adjacent carbon, so it will show multiplied like this. So this is the and the hydrogen which is responsible is 1, so this will be the structure. Now moving towards next, which is this is in chemical shift of 2.2 into 3, so this will have a carbonyl group attached, okay, CH, and like this, okay, so this will have this group, okay, because this is in the chemical shift of this range 2.2 into 3. Now you have a ester linkage over here, you can uh, imagine, because this already told you that these boards are esters. So now how many carbons we have attached? 1, 2, 3, 4. So definitely it is going to be the CH3. Okay, so now you know the structures of D and E. Let's draw their displayed formula. So this is, you have to draw the displayed formula, right? Yeah. So CH3, and then you have CH, then you have carbon, this ester linkage, then you have this structure. So this is your D. I know this part was a little difficult, but these things will be fine with the practice. Okay, so now the structure of E, this is the structure of E. So CH3, CH, CH3, then you will have ester linkage, then CH3. So this is your displayed, these are your displayed formulae. Okay, now moving towards next part. The spectrum of D includes the quartet at this chemical shift. Okay. Spectrum of D, yeah, 4.1. Okay, identify the proton responsible for this quartet on your structure in 1. Okay, by labeling these protons with the letter F. Okay, so you have to identify the protons responsible for this quartet on your structure. Okay, so this peak at 4.1 is due to this alkyl next to sorry, this is due to this alkyl next to electronegative atom. Okay, and in E, this is due to quartet is due to this these hydrogens. Okay, so identify the protons responsible for this quartet, for this quartet on your structure by labeling these protons with the letter F. So um so identify the protons responsible. Okay, so the protons which are responsible for this are these two. Okay, you have to label them by with the F. Okay, these are the your protons which are responsible for these peaks. Okay, now explain why this peak is split into quartet, because there are three hydrogen atoms on the adjacent carbon. So the this will give n plus 1. N is number of hydrogens on the adjacent carbon. So this is 3 plus 1, so it will give a quartet. Okay, so you can say, write that this explain why this peak is split into a quartet, because 3 protons or 3 hydrogens on neighboring carbon. or on adjacent carbon. Okay. Now the spectrum of E has a doublet at 1.1. This doublet. Okay. Now identify the protons responsible for this doublet. Okay. So the protons responsible for this doublet is this proton. Oh, sorry, not this proton. Actually, these protons. These protons. These protons are responsible for this doublet. Okay. Now identify the protons responsible for this doublet on your structure by labeling these protons with the letter G. So you have to label these protons with the letter G. Okay. And explain why this peak has a chemical shift of 1.1. Because you can see that on adjacent carbon there is a one hydrogen. Okay. Oh, sorry. You have to why this peak has a chemical shift of 1.1. Okay, you have to tell the why this chemical shift has this has a chemical shift of 1.1, because this has an alkane environment. Okay, because alkane environment, of course. Okay, so because uh, it has it is alkane, because you can say that the environment, because it has alkane environment. Okay, so is the this is all for the day. I hope everything is clear to you, and if you have any queries you can ask me in the comments. And thanks for everyone for watching. I will see you in the next video soon. And if you haven't subscribed my YouTube channel, do subscribe. Thank you.